Hi everyone, this is Xiaoye from Zhejiang University. Today I would like to introduce our journal first paper, GNN-Context, GNN-based code context prediction for programming tasks. This paper was a joint work of Zhejiang University and Singapore Management University. Developers navigate code to understand relevant parts of code base, forming code context models in their mind. In large-scale software projects, developers must navigate numerous source code files, which lead to complicated code context models and raise the cognitive loads for developers. Here comes the code context prediction, which can help reduce the cognitive burden and enhance the productivity of the developers. Here is an example. A developer navigates through and searches for relevant code elements to perform the bug fixing task in the Mylink project. As a result, he locates two relevant code elements. One is the class code elements, the other is the method code elements, which were captured by the code context prediction approaches as the initial code context model. By learning patterns from interaction histories, this code context prediction approaches form a future code context model by recommending likely code element of interest based on the initial code context model. Here is the SOTA approach for code context prediction task. On the one hand, it generalizes code elements by stereotype roles to learn their syntactic behavior patterns, which capture shallow syntactic and lexical features of code elements. On the other hand, it learns abstract direct graph patterns that encode syntactic relationships among code elements. However, it fails to capture multi-hop structural interdependencies among code elements. Based on these two observations, we adopt code representation learning models to capture deeper syntactic and semantic information of code elements to enhance the performance of code context prediction. We also utilize graph neural networks to capture both structural and contextual information among code elements of code context models. Our approach consists of two phases, the training phase and prediction phase. The training phase takes the code context models and their relevant source codes as input and produce a well-trained GNN model for code context prediction. In step 1, we first build abstract syntax trees and call graphs to capture the syntactic and semantic information of source code. We then utilize programming slicing technique to generate expanded code context models from initial code context model. In step 2, we transform the nodes in the expanded code context model into low-dimensional vector representations. In step 3, we utilize both contrastive learning and GNNs to learn the structural and contextual information of code context models. In the prediction phase, our approach takes the initial code context model of a given task as input and generates the expanded code context model and conduct node embedding for the expanded code context model as it does in the training phase. The expanded code context model and its corresponding vector representations are then fed into the well-trained model as graph inputs for code context prediction. To evaluate our approach, We form a dataset of code context models using the interaction histories captured as developers work with 3 open-source Eclipse projects, MyLink, Platform, and PDE. Here is the data statistics. We quantified the practical value of the predict code elements in the code context models of our dataset. From the table, we can see that over 50% of code elements within the code context models were added at least once. For the remaining viewed-only elements, the average view count is over 1, and the average duration viewing time is over 100 seconds, which shows that the data set we consider as ground truth closely reflects the actual interaction of developers, highlighting the practical relevance of predicting code elements in the ground truth. Figure 3 illustrates an example workflow of our evaluation. We first generate the seed node from the code context model in our datasets. Then we follow the step of program analysis and slicing to generate the expanded code context model from initial code context model. The nodes within the code context model, but not selected as seed nodes, is considered as target node for the prediction. In this case, the target node is the node 3. The code context prediction is to predict the target node, i.e. the node 3, when given the seed nodes. To comprehensively evaluate the effectiveness of GNN-Context, we compare it against 3 baseline approaches. We choose the SOTA approach proposed by one, which is specifically designed for code context prediction. We also choose the leading SOTA for the bug localization and API recommendation tasks, as they share the objective of locating code relevant to a specific programming task as code context prediction. To measure the performance of code context prediction, we choose 2 metrics that are widely used in previous studies, MRR and top-K recall. Here are the results. Our approach demonstrates a significant improvement over the SOTA baseline, achieving average improvements of over 62% and 81% in MRR and R at 5. GNN-Context also outperforms the leading SOTA approach for bug localization and API recommendation. We also conduct experiments in a cross-project setting to analyze how different datasets impact the performance of our approach in code context prediction. The results show that the GNN-Context exhibits promising performance in cross-project settings. Cross-project prediction even outperform within-project predictions, especially when the training data comes from a project with rich and highly relevant historical data. Here in the table, the performance of case 3 to 6 is better than the case 1 and 2. Due to the time limitation, we omit ablation study and sensitivity analysis of our evaluation. If you are interested, please find more results in our paper. We evaluate the different design choice of initial code context models from datasets to assess potential bias in the experiment. We compare the prediction performance of GNN-Context using 2 selection strategies for the seed elements in a code context model. The results show that the order in which code elements are assessed has a negligible impact on the performance of GNN-context. We also explore the reasons why our approach outperforms the SOTA approach in node embedding. Our hypothesis is that our approach captures richer features of code elements through effective code representation learning. We applied a KNN clustering algorithm to class nodes labeled with command as their stereotypes in the SOTA approach. Here are the results. 2 distinct clusters were identified for these nodes with high precision, suggesting that our approach enables a more granular representation of nodes. Future work could further explore advanced code representation learning models to capture more nuanced representations of code elements in code context models. In summary, this work represented a novel approach for predicting code contexts using GNNs, named GNN-context, and the approach significantly outperforms the SOTA approach. For more details and implications, please refer to our paper at the link provided. Thanks for your listening.